In this section, we will introduce manifold and deep learning to show you how we can use this unsupervised learning technique to help you better manage high-dimensional data. Particularly, we'll take a look at the challenges that come with high-dimensional data and the manifold hypothesis that enables these techniques. We'll see linear and linear approaches to manifold learning and take a closer look at t-SNE and UMAP, very recent approaches that enable high-dimensional visualizations. Then we also take a look at the contributions of deep learning to visualizing high-dimensional data in the form of autoencoders. So let's get started taking a look at the goals and benefits of dimensionality reduction and the manifold hypothesis, as well as the goals of applying this hypothesis to unsupervised learning techniques. And then we'll see a few examples of manifolds to get started with the data sets that we'll be using throughout this section. So there's quite a few challenges that come with high-dimensional data, starting with the challenges in visualization and visualizing data beyond 3 dimensions. Even more so, though, there is the curse of dimensionality, which leads to an ever-increasing distance between data points as the number of dimensions goes up. That at the same time means that the space that these data points inhabitate in fact becomes increasingly sparse or empty, and that creates difficulties for predictions. So for instance, this means that this notion of a local neighborhood that you can use to rely on to get predictions for data points inside or around this neighborhood becomes less and less meaningful, because the size of a neighborhood that captures a given fraction of your data becomes ever larger and larger. So for instance, if you want to capture 1% of a neighborhood on a line of unit 1, you only need 1% of that line. But as you go to 10 dimensions, you already need to capture 63% of the side of each unit of what is then a hypercube to just capture 1% of the volume in this 10-dimensional object. So that, since you go over such a large range for each variable, the local neighborhoods are no longer local in any sense. Similarly, another perspective on this is that the data, they are found increasingly near the boundary of the sample space. That creates difficulties for interpolation. You actually need always to extrapolate from data by the boundary. So new data points will it will be difficult to approximate or come up with predictions for them based on sort of interpolating between existing samples. The ability to generate or capture more data to maintain the sample density that would mean that the distances between data points remains constant. It's very difficult to do in practice because the number of data that you need for that increases exponentially with the number of dimensions. So if you need 10 data points to create an average distance of 0.1 on a line of unit 1, in 2 dimensions you already need 100, and in 3, 1000, and it goes up from there. If you then think that the complexity of estimators increases with the number of features or dimensions, which in turn makes these estimators more subject to errors due to variance, then you may see that the curse of dimensionality really directly affects the ability of supervised learning algorithms to make accurate predictions, because one source of error just keeps increasing. And we have just seen that the one remedy that you would have, which is to increase the number of data that you can use, that is not available really because the size of the data would increase so dramatically. Now, manifolds to the rescue. What are manifolds? The idea is that a manifold is a region that is connected that nearby looks like a Euclidean space of lower dimensionality. So, for instance, if you take a line in 2 or 3D, then you have a one-dimensional manifold embedded in a higher dimensional space. That is for a one-dimensional line, or a circle, but it's not really true for an 8 which intersects, which at that point really becomes a 2-dimensional data structure. Another example is planet Earth, which people have thought for quite a while is a flat structure, so 2-dimensional structure, when in fact it's a sphere or so in three-dimensional space, which, locally looks differently. So that is kind of this difference between an object that can look of one dimensionality or can be approximated locally as a lower dimensional object, when in fact globally it is a higher dimensional object. And the manifold hypothesis then posits that essentially all data tend to be close to or nearby lower dimensional manifolds. And that is something that in machine learning is used all the time, because the algorithms that in supervised learning estimate functional relationships between inputs and outputs always assume that interesting variation really only occurs along given manifolds, which is what these algorithms are able to model. Otherwise, the amount of options, potential functional relationships would be way too large, and hence this limitation to a subset of this space of dimensionality n. So how can we apply this? The idea is that manifold learning approximates these intrinsic dimensions, which are fewer than the dimensionality of the data set itself, to capture kind of these key characteristics. And if one looks across many data sets, then it does stand out that few data really vary completely randomly, which would imply that each feature is uniformly randomly distributed and also independent of each other. That is very rarely the case. So that means that in a given sample space, there tend to be locations where it's much more likely to find elements of that population of objects that one is looking at. For instance, images. If one looks at image data with maybe 100 dimensions that represent certain, say, handwritten digits, then it's much likelier to find representatives of a 1 or 5 in certain areas than elsewhere. And not only that, but one can also think that transitions among different objects of one class, like a rotation or a translation of, for instance, an image object, can be envisioned like a slight shift in the values of these pixels, which exactly is what happens as one moves along a smooth manifold in this higher dimensional space. But really, sort of the action is happening only on a lower dimensional space. And then, of course, what we want to achieve is that we find the coordinates of the original objects that live in the higher dimensional space in the lower dimensional space, so that we can represent them more simply. And that, for instance, is what happens on roads, which really are one-dimensional manifolds in three-dimensional space. And we, of course, have come accustomed to numbering houses with a single number, a simple ordering in one dimension, rather than providing three-dimensional coordinates for every destination.